So thank you, the chairman, and good morning, ladies and gentlemen. My name is Fuijun Niu, and working in State Key Laboratory of Frozen Soil Engineering. And I'm very honored to give a presentation on adaptation of transportation infrastructures building on degrading permafrost. And also thanks to Professor Guy Doherty and Hilsey Brooks in Navarre University. They two are co-authors of the transaction paper for this important conference. And the content about my presentation include background, transportation infrastructures in permafrost regions, and also permafrost degradation on the transportation infrastructures. And the third one, engineering development of adaptive capacity, and fourth, full-scale application, relative cost and risk analysis. And then I'd like to conclude my presentation. At first, how about transportation infrastructures in permafrost regions? This figure shows that permafrost distribution in the Northern Hemisphere, and also show the main road that include highway and railroad around the critical regions and also on Tibet Plateau. So transportation infrastructures is essential to social and economic subsistence in so-called polar regions. And also they are very vertical for sparse population spread out thousands of kilometers. In fact, road construction in permafrost regions has more than 100 years of history. Approximately 9,000 kilometers of railroad were operational in permafrost region before the K2R Qinghai-Tibet Railway was constructed. In China, we can see the permafrost distribute about 1/4 of the land territory, and the main part is on the Qinghai-Tibet Plateau here. We call it high altitude permafrost. It is about 7% of the Tibet Plateau land area, and another one is in the northeast China. It's same to the permafrost in Russia. And also we can see many roads and highway in permafrost regions. And here is the oldest railroad in northeast China. How about in Canada? We can see that is the permafrost distribution map and many roads around the north edge of the permafrost area. In fact, the population in northern territory, in northern Canada, is around 500,000. It is a population in Macau, China, so that is a very sparse population in northern part. And in Yukon and the northern West Territory, the population is only 80,000. That is, all the people can be gathered in the National Stadium in Beijing. So the population is pretty sparse. But however, infrastructures, transportation infrastructures is vertical and also sometimes life-supporting infrastructures to local people and the social development. So how about permafrost influencing infrastructure? At first, we know normally permafrost is enriched in ground ice and also sensitive to temperature change. This one is show that on the Qinghai-Tibet Plateau, it is massive ground ice, and ice in cold draining and in Arctic regions. And normally, natural thawing and climate warming and even water or wind erosion and forest fire can cause the degradation. And also, engineering disturbing thawing and the human activities can also cause some hazards like the thermokarst lake and the bimodal flows and the soil fluctuations and the settlement and even landslide. So these kinds of geological hazard can potentially or directly influence infrastructures. Again, we can see the tracks in northeast China is old railway. The tracks is totally seriously, and also the tracks in Baikal Amur Railway and Chara to China Railway is very serious. And also cracks on the Qinghai-Tibet Highway and the cracks and the settlement on the Qinghai-Tibet Highway. And also we can see settlement in Alaska Highway. So soil settlement corrects damage to transportation infrastructures, nearly to all of the transportation infrastructures. Another problem is frost heave, like this one. It is the pole was frost uplifted and the surface is tilted. So soil settlement, frost heave, and even weathering of the rocks can do damages to transportation infrastructures. Anyway, soil settlement is the most serious one. So how about the situation of the existing infrastructures? According to investigation, of the Trans-Siberian Railway, about 30% of the total length was damaged. And also, of the Baikal Railway, the region is over 30%. Of the Qinghai-Tibet Highway, also damaged region is over 30%. So totally, the damaged region was over 30% for existing road before the Qinghai-Tibet Railway was constructed. So permafrost degradation is still an enormous challenge. So how about permafrost degradation? I'm not care about how much and how large area of the permafrost degraded, but our president of IPA, Professor Tony, said it is not permanent. What we know disturbing because permafrost soil is like to be irreversible. So that is permafrost change and the infrastructures around the world, and how about the permafrost degradation on the transportation infrastructures? At first, we can see we have a look about global natural changes, and Lawrence and Slater predicted degrees of permafrost area by 62% and 90% by 2010, 100 and the BY and A2 scenarios. And also recent results show the same degradation. Chinese researchers projected changes in high latitude, and high altitude permafrost regions during the period from 1986 to 2099. And that is mean the degradation will be continued. So one of my colleagues in Alfred-Wegener-Institut studied the spatial distribution of changing rate of the active thickness. We can see the active layer thickness generally increased from the highly continuous permafrost zone to the sourcing discontinuous zone, showing a dramatic in warmer permafrost region than those in cold permafrost region. So how about the degradation caused risks or damages to local infrastructures? And Professor Nielsen showed the pictures about the risk around the Arctic regions and also Tibet regions. We can see the most serious region is around this area, and also on the Qinghai-Tibet Plateau. So how to solve the problems? Again, we use this map, and Professor Jorgensen showed this. It's quite complex. Anyway, from the physical condition leading to permafrost degradation, maybe somewhat about the geology and climate, especially microclimate change, and the vegetation on the surface may be changed. At last, the problems causing to influencing the infrastructures is soil settlement, like removing the peat soil, because we know peat soil on the soil and frozen state, the thermal conductivity is quite different, and also related to water content, and also the surface water gathering. Fortunately, we monitored a thermal karst lake near the highway of Qinghai-Tibet Railway Highway. In 3 years, about 23 meters of the thermal karst frozen soil was disappearing around in 3 years from 2006 to 2009. Here, this picture shows. That means the water gathering on the surface can do influencing to the local factors by degrading of the permafrost. So, because of soil degradation, the physical conditions of the embankment also will be changed. Because of the sowing at the toe of the slopes, the soil will be consolidated, and also because of the slopes on two sides, heat will be absorbed from the slope surface and the embankment surface. Even because of the snow cover, their warming will lead to the degradation also of the permafrost here. So sometimes cracks and caused by settlement will occur, and even sometimes maybe landslide or seriously settlement. In fact, some site monitoring results really proven this. Like this one, it's a site along the Qinghai-Tibet Highway. We can see from 1996 to 2007, all the active layers, thickness of active layer is increasing. And also the deformation is continued. Shown by this one, this is the deformation. And the deformation is well related to sowing rate. So that means with continuous degradation of permafrost, the deformation of the embankment or road bed will be continued. Sometimes maybe unfrozen layer or unfrozen core will be formed under the embankment. So this one is also about the Qinghai-Tibet Highway. From 2001, there's a 4 meters thick of the unfrozen layer formed, and also the deformation of the embankment continued. So we can see the degradation or sowing of permafrost can cause engineering problems, also damages to infrastructures. So how to solve or prevent the problems? We can see some engineering development of adaptive capacity. At first, we have a traditional passive method. In fact, we have studied this kind of a method for a couple of years, and during the past, like this one, the old lady is selling ice lily. He's covered with ice lily with a quilt. But unfortunately, this kind of method cannot solve the melting problems forever, even for a long time. So we tend to maybe increase the thermal resistance, so increase the embankment from the engineering side. But if the embankment height was increased, the slope area will be increased. So heat absorbed from the sunshine will increase. And then maybe the embankment will be lowered. At last, should be a reasonable heat in different regions. Anyway, the passive method, even with using geotextile, can only delay the permafrost sowing, but cannot ensure thermal and dynamic stability of the permafrost for a long time. So what can we do? Can we use artificial ground freezing method? The answer is no, because it's too energy costly. So how to cool down the subgrade and underlying permafrost? As the artificial ground freezing is cannot be used, where to get the cool energy, we turn to the cold earth spot around the world to see what kind of factors influencing the existence of permafrost. Like this way, we can control radiation, to control thermal conductivity, to control heat evactions. Because there's a complex interactions between environment and permafrost and climate and engineering, the only way is to using engineering method and to change the local factors to influence thermal stability and deformation, to control the deformation. So again, we use this system from the geology, climate, especially microclimate and surface. At first, we can change the soil or the rock or some kind of the other materials. And also we can use heat convections like the thermosiphon and also ducts and those like things like holy bricks. And we can change the color of the surface. We can do some sunshine shader and grass cover. So why we control solar radiation? At first, we can see some indicators from permafrost status. This table shows that is the ground temperature at the lowest slope near the west station in Xinjiang province. It is West China. The ground temperature is minus 2.4, and the permafrost thickness is around 100 meters. But on the west and the south slopes, the ground temperature is quite high. So that means to control the solar radiation can greatly influence the permafrost status. In engineering aspect, high albedo surface materials tested along the Qinghai Tibet Highway, but now it is disappearing. And also, numerous surface treatment using light color aggregates in the Beaver Creek project. It is supported by Gidori. And also, high albedo materials tested in Saint-Louis, Quebec. It's about and sometimes maybe the ballast can be painted into white to protect the radiation, prevent the radiation. This one is the testing sections along the Qinghai Tibet Railway. It is constructed in 2003. Unfortunately, the material cannot resist strong wind and high radiation. At last, it is removed. Anyway, about 1 year's monitoring can show that the surface temperature on the sheet is about 4 degrees Celsius lower than the normal status, and also this kind of structures. Similarly, the surface temperature, ground temperature was lowered. And we can see the ground temperature field like this one. This in winter time, normal one here is unfrozen area. On the sheet, there's snow. And just after 1 year, here, the depth of the active layer is around 8 meters. Just after 1 year, it is uplifted to 2 meters. So the effect is very obvious. The second way is to control the heat convections. At first, we still tend to the natural situation. Here is ancient tombs in Kazakhstan. It is about 2,000 to 2,500 years ago. Because of the structures like this, permafrost was found. So there are many sites covered by block, the scree or coal room or talus slopes. We can find ground temperatures different to the nearby area. At least 20 reported cases around the world. The ground temperature is greatly lower than the around the areas. I monitored this one here. Oh, I'm sorry. I monitored this one here in China. It is 200 kilometers far from Beijing and 600 kilometers far from the south edge of the permafrost. The air temperature here is about 7.3 degrees C, but we can see here. So this area, in some regions, there's no trees. And investigated with GPR and monitored work, we can see there's permafrost around these areas. It's under the crust rocks, and the ground temperatures like this. And in winter, from these two boreholes, we can see minimal ground temperature is around -5, and around a year is -1. In summertime, there's no trees, and in winter time, there's holes on the floor. That means air are convecting inside. From this, we can use to infrastructure construction. And this one is tested by Professor Chen Gedong in around 1970s, and the result is quite good. And we used three kinds of different structures: crust rock basement embankment, and crust rock sloped embankment, and U-shaped crust rock embankment. And this one also called air convection embankment, ACE embankment in creek Beaver Creek experiment site. So how about the monitoring result? At first, we can see this one is, the upper one is the traditional embankment. We can see after the construction, the ground temperature is increased. And on the crust rock basement and sloped and U-shaped, all the ground temperature is lowered. Unfortunately, this one, the seismic character is not good because that can cause the cracks. And also same result was gotten at the Beaver Creek site. And the ground temperature monitored over 10 years shows that after first 3 or 4 years, ground temperature at different depths is decreased. How about the structures to resist climate warming? From numerical simulation, we can see if the air temperature increased 2.6 in 50 years, such structures can still protect the underlying permafrost. But the traditional one, this one, cannot protect the underlying permafrost. Third one is, another way is to use duct to ventilating the duct ventilation methods. We used different styles, and these styles in Beaver Creek. Because on the Qinghai Tibet Plateau, the air temperature, when the air temperature is high in summer, the wind speed is quite low. But in winter time, the wind is very strong. Maximum speed will reach 30 meters per second. But the temperature is very low. So we use these properties to cool down the embankment. And the result from the Beaver Creek, also we can see the sowing depth was lowered. And also, just after 1 year, the traditional the permafrost temperature on the traditional embankment is quite high, and on the duct ventilation embankment is quite lower. This one is also Professor Gidori called the heat gene structures at Beaver Creeks. Similarly, the mechanism is same to let air convected flow into the embankment to cool down the soils. The third one is to control thermal conductivity. As I said, the pit soils, the conductivity is different on different temperatures and water content. Also, maybe we can use the offset at the surface. This one is shown along the Qinghai Tibet highway, railway. Here is covered by grass. The ground temperature is quite lower, and these form materials is somewhat warmer. Without anything covered, the ground temperature is quite high. So it is a kind of a passive one, can resist a kind of the warming, but at last it will fall. And also thermal insulation layer was used. We can see it just cut down the rising the range of the temperature changes. Another way is to use thermosiphon. Anyway, this one is very expensive, but it is effective. We installed a lot of thermosiphons along the Qinghai Tibet highway railway because the ground temperature on the Tibet plateau is quite higher than in Arctic regions. When the thermosiphon installed, the ground temperature was greatly decreased from borehole monitoring at different depths. If the condition is very complex or very difficult to solve, then dry bridge can be applied. The longest dry bridge of the Qinghai Tibet Railway is 11.7 kilometers long. It is in warm and ice-rich permafrost. And the second one, we can use the combined method to cover the surface with crust rock and thermal insulation, and also combined with installed with thermosiphon. Anyway, all of the duct ventilation, crust rock basement embankment, and crust rock embankment thermosiphon along with insulation can be used under such conditions. The mean annual air temperature is minus 3.5, and even 2 degrees C increased in 50 years. This method can still be effective. So how about the full-scale application? The main infrastructures in permafrost region, like Trans-Baikal Railroad, it is nearly 120 years old, and Alaska Railway is nearly 100, and the newest one is Qinghai-Tibet Railway. Of all these roads, the highest rail speed in the permafrost region is Qinghai-Tibet Railway. It's reached 100 kilometers per hour and reached the design objects. Along the Qinghai-Tibet Railway, 142 kilometers of air convection embankment throughout the embankment, and also 156 kilometers placed along the side slopes, and 30 kilometers installed with thermosiphon. That means totally the permafrost region distance is 550 kilometers long. Most embankment was constructed with active cooling method. And also it is tested in two large-scale adaptation in Nuvik and also in Salut airport testing sections. And some test risk investigation and evaluation along the Qinghai-Tibet highway was done. Like the settlement series is different, and there's transversal cracks, and longitudinal cracks, and net cracks. So we need some cautions. Risk analysis about climate warming. At first, the Qinghai-Tibet Railway was designed without considering about climate warming. About 1 year or 2 years later, 1 degree C in 100 years were considered, and then about $0.5 trillion was added. Another one is environment change and weathering, wind blowing sand, and snow covering can influence the cooling effect. Like this one, rocks are weathering, and the porosity will be decreased, and the convection efficiency will be decreased. And then we moved to primarily to cover the crust rock surface with geotextile and soils to prevent the blowing sand. And in the future, maybe superhighway will be constructed, and we designed different structures like this one. Here's crust rock, and in the middle side is also crust rock, and we can install some tubes to let the air to be flowed into the embankment. Cost analysis is quite difficult to see that which one is most expensive. Anyway, ACE, that is air convection embankment, can save a lot of the money. So at last, I'll give some conclusions and suggestions. At first, the climate warming and the change of the local factors influencing the development of permafrost have been leading to degradation of permafrost and resulted in instability and even damages of the infrastructures. Expensive maintenance and reinforcement urge the traditional engineering methods of increasing the thermal resistance to change into actively cooling methods. Learning from the latter is very important. The method based on the cooling principle include using high albedo surface materials, sun shades, air convection embankment, air ducts, heat stream, thermosiphon, and geosynthetic reinforcement showed a positive effect of cooling the underlying permafrost, especially along the Qinghai-Tibet Railway in permafrost regions. A cost and effectiveness analysis was completed for the Beaver Creek test. Still little information is available. With regards to the relative cost of each adaptive strategy, lowering the maintenance cost during the primary design is encouraged. It is suggested to truly consider the influence of the continuous climate warming on permafrost degradation and the lifetime service in designing and construction of new transportation infrastructures in permafrost region. And last, maybe suggestions for IPA to set up an international workshop for investigation on guidebook is necessary. And thanks for your attention.